If you know me, you probably know that I have a lot of classification problems. Some in my personal life, but mostly at work. I started from just running a list of classifiers, and while some work better in some cases and others are better for other cases, XGBoost consistently performs very good. I was really excited to see that because XGBoost is a tree-based model, and I really like trees. In nature, of course, but also in machine learning. They're really easy to understand, the kind of machine learning model you can tell your mom about. So I wanted to understand how Extubus works and why it performs so well. My name is Yama Anin Aminof, and I am a data scientist and a musician. I work at MyPart, a startup in the music industry. Today I'm going to share with you my journey with tree-based classifiers while tackling the problem of classifying songs into different genres. The first thing we're going to talk about is the dataset and the process of extracting features from songs. Then we're going to see how to build a decision tree and how it performs in this case of genre classification. Then we'll dive into XGBoost and see how it improved our results. And we'll finish with a comparison to other machine learning models. There are many ways to build a dataset for the problem of genre classification. The dataset we will see today is from Kaggle. We have 4 genres: pop, metal, blues, and classical music, with 100 samples from each genre. The features were extracted using Librosa, which is a Python package used for music and audio analysis. The features we're using are rhythm features and spectral features, which are features that are based on the frequency of the signal. Rhythm features include the estimated tempo, which is the speed of the song. That can be extracted from a tempogram. On the y-axis, we have the BPM, beats per minute, which is the way we measure tempo. The x-axis is the time. And here we can see how the tempi, which is the plural of tempo, changes over time. Spectral features include the spectral centroid, which is the weighted mean of the frequencies in the signal, with the magnitudes as the weights. For some of you, it might make sense to think about it as the center of mass of the spectrum. So how do we get those frequencies and magnitudes? We have a very nice function called Fourier transform that extracts the frequencies from a given signal. Of course, there's a lot more to get into all of this, but for today, that will do. So now that we have the features and the classes sorted, let's talk about decision trees. A decision tree asks questions and then separates the data by the answers. For example, if we want to build a decision tree for a binary classification between metal songs and non-metal songs, we can ask if the song is very loud. And since most metal songs are loud, we'll have more metal songs on the left and more non-metal songs on the right. But metal songs are more than just loud. And we can also ask questions that their answers are not binary. For example, if we want to ask something about how fast the song is, we can use the BPM we mentioned earlier, beats per minute, and we can ask if the song's BPM is larger than 100. And since most metal songs are faster than that, that should give us better separation between the classes. The first split is called the root node of the tree. Other splits are called nodes, and the final classification is coming from the leaf nodes, where we see the classes metal and not metal. So at each point, we want to find the best split for the tree. What does it mean, the best? The one with the lowest impurity. A leaf is called pure if the samples that reach it are all from the same class. For example, if we look at all the songs that are not loud, we have 10 metal songs and 19 non-metal songs. So the probability of a song that reaches that leaf to be a metal song is 0.1. And the probability of a song that reaches that leaf to not be a metal song is 0.9. We can add these probabilities to every leaf node. And we can see that only one leaf classifying songs as not metal is pure, which means that in our dataset, all songs that are loud and slow are not metal songs, while the 2 other leaves are impure, since they consist of both metal and non-metal songs. There are many ways to measure impurity, And a common one is called Gini. In classification problems, the Gini impurity of a leaf is calculated using the probabilities of samples that reach that leaf to be in each class. In our case, the Gini impurity of a leaf is 1 minus the probability of being a metal song squared minus the probability of not being a metal song squared. So we can calculate the Gini impurity for each leaf node. Trust me, I've calculated it for you. These are the numbers we get. The next stage is to calculate the Gini impurity for using a specific feature and a specific threshold for the split. And this is equal to the weighted average of the leaf node impurities. The weights are the ratio of songs in each leaf, so that if one leaf consists of more songs, it will get more weight. So if the leaves under the BPM split consist of the same number of songs, the Gini impurity for using the feature BPM and the threshold 100 is 0.21. And if we calculate the Gini impurity for a split with the same feature BPM but a different threshold 70, we'll see that the leaves will be less pure and the Gini impurity of that split will be higher. So we should choose the threshold 100 over the threshold 70. So for every split we want to add, we just have to go through all of the options for the splits, calculate the Gini impurity, and choose the best one. If we have a binary feature or a categorical one, it's easy to go through all of the options. But if we have a numeric one, it sounds a bit confusing because we can't go over all of the numbers. One thing we can do is order all the values in this feature, calculate the average between each two values, and use those averages as the potential values for splits. So now that we know how to build a decision tree, let's see how it performs on our classification problem. Remember that it's classifying sounds into 4 genres and not just metal. So we get 81% accuracy, which is very nice. But can we do better than that? Since I love trees so much, I went through some more tree-based classifiers, like random forest and XGBoost, that improved the results, but not as much as Extubus. Extubus means extreme gradient boosting. Boosting is an ensemble method that helps reduce bias and variance. It converts weak learners, which are models that are just better than random guessing, like decision trees, to strong ones, which are models that are much better than random guessing, like XGBoost. If we're doing a binary classification, trying to predict if a song is metal or not, the values of the labels are 1 for metal songs and 0 for non-metal songs. Of course, we have more features and more songs than what we see in this table. Extubus starts by giving one initial prediction for all of the samples, the same prediction, and its default value is 0.5. So the default prediction is that there is a 50% chance that the song is a metal song. Then we calculate the residuals, the difference between the labels and the predictions. So for metal songs, we get 1 minus 0.5, which is 0.5. And for non-metal songs, we get 0 minus 0.5, which is minus 0.5. And we call them our new labels. And then we build the first tree. That tree tries to predict the new labels. How do we predict the labels if they're numbers and not classes like we saw before? If we split by loudness, we look at all the songs that are not loud, and the prediction we put in the right leaf is the average label of these songs. In this case, it's one song and its label is minus 0.5. Then when we split by BPM, again, we get on the right leaf one song that its label is minus 0.5. On the left leaf, we get 2 metal songs and 1 non-metal song. So the prediction is the average of 0.5, 0.5, and minus 0.5, which is 0.167. And just like we saw in the decision tree, we have a measure that helps us choose the best split. This time, it's trying to minimize the residuals, the difference between the label and the prediction that results from each split. So when we want to use that tree for prediction, we add its prediction to the initial prediction. So if a song is fast and loud, its prediction will be 0.5 plus 0.167, which is 0.667. And that is the general concept. Every time we calculate the new residuals, which are the labels minus the predictions, and build a new tree that tries to predict those residuals. And for prediction, we add the initial prediction to the prediction of each one of the following trees. Each tree gets us a little bit closer to the real value. So actually, we're not just adding all of these predictions as they are, but also scaling them by a learning rate, which is a parameter called eta, and its default value is 0.3. So what is the learning rate and why do we need it? We said that each tree takes us one step closer to the real value. The learning rate says what is the size of the step we're taking. The smaller the step is, the closer we can get to the best model, but it's slower computationally because we have to take a lot of steps. For example, if there's ice cream 1 meter and 43 centimeters away from me, and my step size is 1 meter long, the closest I can get to the ice cream is 43 centimeters away after taking one step. But if my step size is 10 centimeters long, I can take 14 steps and get 3 centimeters away from the ice cream. And of course, if my step size is 1 centimeter long, then I can get exactly to where the ice cream is and eat all of it. Just like in life, we can improve tremendously by taking a lot of small steps towards our goals. And it's not just inspirational, it results in lower variance, so we'll perform better on different datasets. The last subject I'm going to talk about regarding Extubus is pruning. Pruning is the process of deleting splits from the tree. Doing that helps us reduce the complexity of the tree, improve accuracy, and reduce overfitting. In Extubus, after we finish building each tree, we move to the stage of pruning that tree. When we built the tree, we calculated the gain, which is sort of similar to the gaining we mentioned in the decision tree, that helped us pick the best feature and threshold for each split. Now we use the gain to decide if we're keeping that split or pruning it. We choose a threshold, and if the gain is below that threshold, we prune the split, else we keep it. If we prune a split, then we will go backwards up the branch and test the split above it as well. It's possible to have a split with a smaller gain as a parent of a split with a higher gain. And that's what's nice about pruning after the tree is completely built. We won't miss that lower split with the higher gain, even though its parent has lower gain. So we talked about the initial prediction Extubus gives, the trees that predict the residuals, scaling the predictions by the learning rate, and pruning the trees after they are built. Of course, there's a lot more to say about Extubus, regularization and optimizations, but for now, let's talk about performance. I ran Extubus on my dataset of genre classification and got the amazing improvement of 92% accuracy. Much better. Remember the two features I mentioned in the beginning, tempo and spectral centroid? When I looked at the feature importance of these two models, I noticed the decision tree didn't use them at all, while Extubus used all of the features. So just a few points of comparison between tree-based models and other models. One good point to start with is interpretability, since it's such a hot topic. Tree-based models are easier to interpret than many other models. SHAP, for example, which is the library used to explain individual predictions, has a specific solution for tree-based models, which is faster and more accurate than the solution for other models. Also, it's easy to get feature importance from tree-based models, and sometimes not so easy from other models. Another subject that is a sore spot for many people in the industry is the amount of data needed. Tree-based models require less training data than neural networks, for example. And lastly, to make sure you don't think tree-based models are perfect, they only work on tabular data, so we can't use it for other data types like image, text, or audio. Now we can all go back to running XGBoost and enjoying the good results when we understand a bit better how it works. You're welcome to contact me on LinkedIn, and thank you for listening.